Hello and welcome to the 7th episode in my Pygame tutorial series. In this episode I'll be covering infinite worlds and optimization, but I'll be really focusing on where those two ideas intersect and basically how I tend to structure my tile-based games, or just games with a lot of content in the worlds in general. It doesn't necessarily have to be like grid-based tiles. I have this drawing up in MS Paint right now, and it's so I can give an explanation of what exactly I do, because it's a little bit complicated. So if you're familiar with Minecraft, things are broken down into chunks, and I do something similar, and I use that to make it easier for the game to load up what it needs to show. It's easier to handle that information in large chunks when it's like broken down a bit. So what it is like each chunk contains like a certain amount of tiles. In the example I'll be doing today, I'll be using an 8x8 chunk. So each of these squares in here represents a tile, and these green ones are like grass or something, and the brown ones are dirt. And then that all of these tiles are stored in a single like list, and that list represents a chunk. And then the chunk is assigned a coordinate, and a bunch of chunks together make up the world. When I'm rendering stuff, I look for what chunks would be visible inside the game's window and render those. You can calculate what they are by calculating what coordinates of the chunks should be visible in the window. You can figure out what those are, and then you can search a dictionary that's full of chunks and get those and render them. So you don't have to go through all of these chunks that you're not really showing. So if you remember our old example, I used a just like a list and like a map file. This is the map file, and it's stored in a list, which is created like with this function right here. Go right here, I can do print game map. So it's kind of hard to see here. Let's see if I can change this to the right size so you can see this. Okay, I had to go a little bit off the screen for this. There's two layers of lists. There's one list that contains a bunch of other lists that represents rows of data, and each row is like a y coordinate. So you can kind of visually see the map here. That's the old system. And the issue with this is it's hard to add stuff to the map and remove stuff from it. So in an infinite world, you want to be using a dictionary because it's just a lot easier to add to it and not worry about dimensions and stuff too much, because you have to like update the list dimensions and stuff when you do infinite worlds with lists. It's just not really a good idea. So to switch to this dictionary format, first thing I'm going to do is switch the game map itself to an empty dictionary. It's going to be infinitely generated, so it'll fill it up as it goes. So I can just start it off empty and it'll fill it up as it needs stuff. In this example, I'm going to be just kind of hard coding a flat world with some grass in it. In the future, I'll probably do a video on how to do this with Perl and Noise to get a better world generation with like hills and stuff. So here's the old tile rendering code. I'm going to need to take this out. This tile rect stuff is for collisions, and I add to that to mark things that the player can collide with. So I don't need to remove that list. So tile rendering goes here. And then I go up here, and then I need to get rid of this load map function, because we don't need this anymore. But what I will add is a generate chunks function. But before I do that, I would like to show the grass image I'm using. Where is it? Well, it's a plant. It's this thing. So the white's going to be transparent. And yeah, it's just kind of some grass, so that it's not just flat. I mean, it's going to be flat, but there's going to be some grass as decoration. So if you remember back to my earlier drawing, I mentioned that the chunks contain a list, and it's going to have a list of all the tiles inside of it. So while the list of chunks is a dictionary, each chunk is a list full of tiles. So it goes the whole world, the chunks, and then the tiles within the chunks. So when you're generating a chunk, you're going to want the chunks data, which is going to be an empty list by default. And let's set the chunk size. So the chunk size is 8. Like I said, I was going to do chunk size, so I have 8 for this video. So now we have to iterate through all of the positions that could be in that 8 by 8 chunk. So you can do for a Y post and range chunk size. So that'll go 0, 1, 2, 3, 4, 5, 6, 7. So that's 8 values from 0 to 7. And then you put another for loop in here for X. And this generates every single coordinate inside of here. However, that's just the coordinate relative to the chunk. Each chunk has its own location. So the tiles themselves should probably, you don't have to do this, you can adjust it during the rendering. But I like to store the correct rendering location in the tiles data itself. So you should probably set up the real position for the tiles when you create them. So I'm going to create a target X equal to the X value that's inputted for the chunk's location, and then multiply that by the chunk size. This is because if you're on chunk at location 2, 2, that means that there's 16 tiles until you've hit the location of 0, 0, like on your left and above you. Well, above the chunk and to the left of the chunk. So this is how you add the amount of tiles that this location represents to the location of the tile you're rendering. And then you add the location within the chunk. So if I go back to this thing, say I'm rendering this chunk. This chunk right here is at location, let's say 1, 1, because it's 1 to the right and 1 down. But you know that there's 8 tiles above it from this chunk. So to calculate the Y position of this top tile right there, you would multiply the chunk size by the amount of chunks away from 0 it is, which is what I'm doing here. And then you add the specific location within this chunk. So in this case, that's 0, 0. So this would be plus 0, Y, and plus 0, X, as X pose and Y pose. So I need to just do this for Y now. And when you're doing this type of stuff, you need to store the tile type in the tiles data, of course. So by default, it's going to be 0, which represents air. And now I'm going to do a bunch of if statements to represent other tile types. So I'm going to say if target Y, and this is like the true position of the tile, the combination of the chunk's location and where it is within the chunk. So if this is more than 10, the tile type equals 2. That would be dirt, I believe. Yes. LF target Y is 10. That's exactly 10. So that's the layer of tiles directly above these ones. It'll be tile type equals 1. This is grass. And then LF target Y is 9. That's a layer above the grass. I'll do if random.random 1 and 5 is 1. It's a 1 in 5 chance of this happening for every tile that falls under this location. Tile type equals 3. This is for plants, so it's kind of like dotted across the top of the terrain. So this is the plant. This is the grass. Dirt. Nothing. So if the tile is nothing, I'm not going to add it since it doesn't need to be handled at all. So if tile type does not equal 0, then chunk data.append, and then you have to create a new tile. So first I'm going to do the tile's location, and then I'm going to add the tile's type. And now you just return the chunk data. This section right here goes through all of the locations in the chunk and generates the appropriate tiles for that location. In certain chunks, there will be no tiles because all of them will fall under the 0 category because the chunk Y is too high up. Well, technically it's going to be a low value. So chunks will be stored kind of in something like this. So the string right here represents the location. You use this location to find the data of the chunk for rendering and stuff. And this is why it works a lot better than lists, because you can have missing chunks and you can just add them whenever. You don't have to adjust the size of the lists and stuff. So of course our game map's going to be empty by default, so we need to add chunks as we need more chunks. And you can do that when you're rendering, so that you only add chunks as they would appear on screen. So I'm going to do the rest of that in one shot. So if we go back to this picture here, let's get rid of this. You can see that there's a certain amount of tiles that appear in here. Depending on the size of your window and the size of your chunks and stuff, you can calculate how many chunks will be visible in the window. And in this case, you can always assume that there's going to be 3 chunks, well, at most 3 different chunks along the y-axis in the window, and 5 chunks along the x-axis in the window. So in our case, we've got a 600 by 400 window, but our display is actually 300 by 200, and since it's scaled up, we only have to account for that 300 by 200 value. Our chunk size is 8, and our tile size is, I believe, 16 by 16. If you go back to here, you can see down here that it's 16 by 16. So you can go into a calculator and do 16 by 8, and that's how many pixels are in each axis of a chunk. So it's 128 pixels wide and 128 pixels tall. So to find the amount of chunks on each axis that will be visible in the display, you divide the amount of pixels on each axis by the amount of pixels in each chunk. So you do, in our case, 300 divided by 128. So we get 2.34 for the x-axis, and I'm pretty sure it's, I should see, 200, yeah, it's like 1.5 for the y-axis. So you always want to round up on this, and then just for alignment purposes, you want to add 1 to that value too. So because we've got 1.5 for the y-axis, well, 1.5 chunks visible on the y-axis for this project, you round up to 2, and then you add another 1. I'll show you what happens if you don't add 1 here. So yeah, let's just go with the 3 and 2 chunks for now, and I'll show you what happens if you don't add that extra chunk. So for y in range 3, and for x, it's for y in range 2, and for x in range 3, you do target x. This is the location of the chunk, which is on a different scale. It's going to be x, so this is like just the relative location based on the window, and then plus an integer. You don't want a decimal for this. The scroll value, so like where the camera is, divided by the chunk size by the tile resolution. So this highlighted section here is the pixels in a chunk. So, and since scroll is in pixels, you're basically calculating where the top left of the screen is, like what chunk the top left of the screen is in. And adding this X is how you get all of the chunks that are visible on the screen, because you're going through all of the X and Y locations of the chunk visible on screen. Then you do this for Y, and switch the scroll to the Y-axis scroll, and the target chunk equals string of X plus that plus string of Y. So that'll come out as like 1, 2, or whatever. And those are the keys for the dictionary to access the chunks. But this is also where we can generate chunks if they don't exist. So if target chunk not in game map, so if it's not in the game, you can generate it with game map target chunk equals generate chunk, and then you input the location of the chunk, which we just calculated as target X and target Y. And that line right there will generate chunk. Well, those two lines generate chunks if they don't exist yet. And they'll only generate them if they're visible on screen, because this section right here calculates the chunk IDs that are visible on screen. Then you can iterate through the tiles that are stored within the chunk, because remember, if it doesn't exist, it's created right here, so there'll always be a chunk available here since you just generated one if it's not there. And you display the tile. And I'm going to create a tile image index because we're starting to get more tiles. There's 3 of them now. So tile index, tile 1, tile 0, 0 by 16 minus scroll 0, tile 0, 1, so the Y position by 16, the tile resolution, and then the scroll offset. So the tile space position with and then multiply it by the size of the tiles, and then modify the position based on what the camera is seeing. And if the tile type is in 1 or 2, this is grass or dirt, you want to add it to the physics stuff that the player can collide with. So that should do it. I just need to add the tile index thing that's right here. So the tile index is just going to be a dictionary with the keys being the ID of the tile, so like 1, 2, 3, and then the value associated with those keys being the image. So I'm going to go up here. I need to load the plant image. Just pygame.image.load plant.png. I showed you this earlier. .convert because it's got transparent sections. So you gotta convert it before you can add a color key, and then we add the color key of white so that all the white pixels turn to transparent. And then our tile index is going to be 1 for grass image, 2 for dirt image. Remember, 0 is just nothing. And then 3 for the plant image. Okay, so I made a mistake here. This should not be X. That's target X and target Y. So you probably noticed that when I was writing that I didn't, because these are the calculated locations of the chunks. And so this is what happens when you don't add that extra chunk. So now we need to add that extra chunk. Well, first of all, if you notice, a lot of that was on the left, so you do -1 for that, -1, and then that. So the reason why you subtract is because the locations of each chunk is the top left corner of each chunk. So all the tiles in a chunk are to the right. So the top left corner of the chunk can be off the screen, so it won't show the tiles from that chunk. So you gotta do -1 to account for that. So now we can go left, and we can go right. You can see there's an issue right there. I believe that is just the rounding difference between positive and negative chunks. So I think the issue with using int is that it truncates. It chops off the decimal rather than rounding. So let's round that now, and I believe that should get everything loading properly. Yeah, that works properly. So if you, for those of you that don't know, if you do int 0.9, that'll give you 0. But if you do round 0.9, it'll give you 1. Sometimes it'll will give you like a 1.0, so you gotta turn that into an integer because we're using this as an identification type thing. So yeah, this needs to be an integer. But that's pretty much it for the tile system I use. So I mentioned that this video is going to be on optimization, and that was just one example of optimization. At its core, optimization is things like only handling and rendering what's visible, and sorting data so that it can be accessed in as few operations as possible. And sometimes you can do stuff like reducing calculations to be periodic instead of like every frame. In this instance, we rendered and handled the tiles that were on screen, and we also set up the data using the structures of chunks so that it can be accessed in very few operations by the game, so that you can have tons of chunks, but it'll still handle it pretty well. One other thing you can do for optimization is, this doesn't make your stuff run faster, but it helps when your stuff is running slowly. You can set up a game to process stuff independently of the frame rate so that things don't slow down when the frame rate gets slower, because most people, when they're starting off, and I actually do this in a lot of my games too, I set up stuff to be processed every frame, and it's by a specific amount every frame, but there's this idea where you measure how much time passed between each frame and use that to calculate how much the player should have moved. So it doesn't matter how many frames you've handled, you'll still have the player moving at the same speed in real time. It's like you can be going at 5 FPS, but it'll still cover the same amount of distance in the same amount of time as going 60 FPS. Whereas in something like this, if I switch it to like 10 FPS, you can see everything goes super slowly. I'll probably do a video on frame rate independence sometime in the future. Also, one other thing is that parallax background does not apply to this whole thing. If I go over here, it's gone. You can automatically generate those too as you go, as the player travels. You just gotta keep in mind that the coordinates of parallax elements get a bit wonky because they're not you're applying them at certain ratios and stuff. So that can get a bit messy to deal with, but yeah, it's not too hard to implement infinitely generating parallax backgrounds. So that's pretty much it for this episode. In the next episode, I'm going to be basically cleaning up the code and stuff and putting it into more of an object-oriented type of setup, and I'll be implementing my own framework that I use for most of my games into this project, so you can see what that looks like. And it'll also help anyone who looks at the code for my games to understand what exactly I'm doing, because it's going to be the same stuff. After that video, I'll start branching out onto much more advanced topics in the area of Pygame, or just programming games in general, because a lot of these ideas can apply to any language. Anyway, if you have any questions, you can head over to my Discord and ask them there. I've got a dedicated channel for that. And If you're interested in my projects, you can go to my Twitter and see what I'm up to. I'll see you in the next video.